Hello everyone, I hope you're fine. We are the team number one, and today we are here because we are going to explain the first practice hydrogen bonds, hydrophobic and hydrophilic interactions.
This presentation will be separated into five parts: an introduction, the methodology, a display of the results, a discussion and analysis of the results, and finally the conclusions. To give a little bit of context, we'll be answering the three following questions. The first one is: what is molecular dynamics? The second one: what is GROMATS? And the last one is: what is the objective of this lab practice? Molecular dynamics are a computational simulation method that allows us to analyze molecular interactions at the atomic level. The simulation allows us to analyze the change of a molecular system through time, and this is accomplished by calculating the forces between atoms using the Newton's equations of motion. Through molecular dynamics, different cytochemical properties of the system can be calculated, such as the free energy, entropy, solubility, viscosity, pressure, and temperatures of change of phase. One of the most widespread tools for carrying out molecular dynamics is called ROMATS. This is a versatile package for performing molecular dynamics that is simulating Newtonian equations of motion for systems with hundreds of millions of particles. The objective of this lab practice is to evaluate the effect of temperature on the viscosity of water using molecular dynamics in ROMATS. We'll be using a sample of a 4 nanometer box for this lab practice.
And then we will present the methodology that we use in this lab. Okay, we used a box of 4 nanometer system. It's called box because at the initial moment of the simulation, the system has the form of a box. But when the simulation is running, the molecules of water can go anywhere. Then we had to extract the results from the WinRAR folders. And then we have three folders, one per each temperature. For the structure of the procedure, we have first to minimize the system by reducing the potential energy to simplify the simulation. Because if we don't do that, the simulation won't run. Then we had to do the warm up stage by adding temperature to the molecules to add kinetic energy to the simulation. Then we have the equilibrium stage, in which the molecules can freely move in all the system to balance the the kinetic energy of all the system. And finally, in the production stage, as the molecules are moving, we can measure the pathing or the trajectory of each molecule to finally get all the values and all the viscosity values. As I said before, the simulation was set at three different temperatures. Was at 303 Kelvin, 333 Kelvin, and 363 Kelvin. And as we can see here, we have the animation that was run in BMD to see the molecular dynamics like in real action.
So to display the results, we separated them into four different groups. The first three are the stages. So the warm-up stage, the equilibrium stage, and the production stage will be analyzing the kinetic energy, the potential energy, and also the temperature versus time. Um, and for the production stage, we'll be also analyzing the graphics that involve the energy due to polar interactions, apolar interactions, and also the total energy. And for the last part, we'll be analyzing the results of viscosity. The kinetic energy in the warm-up stage grows constantly, and as we can see, the bigger The higher the temperature, the higher the slope, which means there's a higher kinetic energy, the higher temperature there is. The potential energy in this stage shows an initial constant growth for every uh, different temperature, but as we reach a certain time, um, the tendency increases and it gets a little bit more exponential. So there's more potential energy as time goes by. In this warm up stage, the temperature through time keeps increasing constantly, and there are no variations. In the equilibrium stage, the kinetic energy starts to oscillate for every temperature. But as we can see, there's a higher kinetic energy, the higher the temperature there is. There between the oscillations, there are certain peaks, but there's no tendency between the graphs. Just as the same with the kinetic energy, the tendency is like an oscillation with small peaks. This one has less variations, but either way, it has no tendency and it just keeps oscillating through time. The same thing happens for this temperature versus time. There's just oscillation between there's just oscillation through time, so the temperature is not constant, and but it oscillates near the wanted temperature. For the production stage, the kinetic energy has way more oscillations, and so it makes it look like there's just a big strand for every single temperature. But as the same as the other stages, the higher the temperature, the higher the kinetic energy. The potential energy for the production stage also oscillates way more than the stages before, and but has fewer variations than the kinetic energy. It also follows the same tendency that the higher the temperature, the higher the energy. This graphic shows the temperature versus time in the production stage, and it also shows like the same tendency of oscillation through time. But in this case, there is a bigger oscillation the higher the temperature there is, so it isn't as stable. The energy due to polar interactions follow the same principle as the other energies before. The energy due to polar interactions have big oscillations, and so they don't have the same tendency or aren't as precise as the polar interactions. And in this case, there's more energy the lower the temperature is. So it's like the reverse of the polar interactions. This graph of the total energy shows the same tendency that we saw from the start. So as we can see, the higher the temperature, the higher the energy intake per time. For the viscosity results, we had four different samples taken in three different temperatures, and we calculated the average out of the four samples to have like an average viscosity. So as we can see, the lower the temperature, the higher the viscosity.
From now on, we are going to begin to explain what we can extract from the information in the graphs. So let's see. Fine, so let's start talking about the warm-up stage. If you remember in the last slides, we had three graphs from this process: temperature with the time, kinetic energy with the time, and potential energy with the time. And in all of the graphs, we have a tendency to increase the energy over the time. In a specific data, we had the highest energy is obtained at 363 Kelvin and a time of 100 femtoseconds. We can say with confidence that there is a directly proportional relationship with the temperature of the system and the respective energy. Unlike the previous process, what we can observe in the equilibrium stage is that the energy seeks to be as stable as possible, because in the third, the three drops temperature, kinetic energy, and potential energy, we can we can observe a tendency to seek the lowest energy over the time. Um, so what we can observe is how after increasing energy a bit, the energies tend to stabilize. Again, in this process, we also observe that the higher temperature, the respective energies are higher. The production stage, the last stage, it has six parameters and six graphs, of course: temperature, kinetic energy, potential energy, dispersion energy. It is van der Waals interactions, electrostatic energy, Coulomb in the interactions, and the total energy, that is the sum of all the energies. Um, in these graphs, we have like a noise, and this is due to the dispersion of the data and the large amount of data. We have 10,001 information from the time in femtoseconds. And this high dispersion of energy pues, is difficult to interpret. But we can see the parameters between the change of energy, and we can observe that the total energy is more stable than all the others. So it is a positive result. Okay, a discussion about the viscosity in a relation with the temperature. In these graphs that it was made from Minitab, we have contrast between the average viscosity, that is average from all the data that we had from the SIP, and the temperature. uh, we have a directly proportional relationship between the viscosity and the temperature, because we can see that higher temperature equals to higher viscosity. But that's not all that we can say about the viscosity. Let's see the next presentation. From this analysis, I used literature to know what is the viscosity, the average viscosity into reality at 27, 30 Celsius degree. And we have that viscosity in centipoints is 0.76. However, we have an average viscosity from 0.23. So the relative error above the tolerance is, it is unacceptable, because it's over the 5%, and that we can see is that it is too far from the reality.
And finally, we are going to present the conclusions of the lab report. As we could saw in the analysis of results, the viscosity shows a linear pattern that decreases when the temperature increases. About Romax, as we saw in the kinetic energy graphic in the warm-up stage, it has a sudden increase of temperature. Then, in the equilibrium stage, the simulation registers how the system tried a lot of times to reach the minimum energy state. That's a good sign about the program that we use in the simulation, because those are things that happen in real life. Then the viscosity didn't reach satisfying values in comparison to the literature ones. We can reflect that in the fact that we had around 68% of relative error. And we believe that happened because we have few molecules of water in the simulation. We had around 17,000 of molecules of water in comparison to, for example, a glass of water that has millions and millions of molecules. And probably those are like the examples that they used in the literature to take the value. And here we have the references that we use in this report.